Next, we will discuss certain kinematical consideration of fluid motion. Now, we have already assumed that continuum hypothesis, that fluid is a continuous medium, which of course, as you have mentioned earlier, is quite natural because in fluid dynamical analysis we are not concerned with what is happening in the microscopic level or in the molecular level. Now, the first consideration in kinematics is of course to describe the fluid motion. For solid and rigid body, which you are quite familiar with, the obvious description is the velocity of the body or the velocity of a particle. For a body which is usually used as the velocity of the center of mass. The same approach can of course be used also, that here also we can define a material element of fluid and then define its velocity. In that case, how do we define the velocity? For a particular fluid element, we identify the fluid element by its initial position, that is the position that it was occupying at certain time t 0, and then how at subsequent time its position vector is changing and the rate of change of that position vector is the velocity. So, this type of description, if used, is called Lagrangian description. So, this Lagrangian description, what we do is velocity of a material fluid element. When you see element, what we mean is basically an infinitesimal volume of the material or of the fluid here. Infinitesimal in macroscopic sense, not in microscopic or molecular sense. And the position vector of a particle which was at say at a location, initial location of the particle, that is the identification, location at say time t 0, then the position vector with respect for that you may denote it by anything say called x for that fluid element which was at, let us denote it as this, then at a subsequent time which was at a and t 0 and the velocity is as you have already defined, let us call this to be v or v I is as before your this. Very simple description. However, this description is not very popular in fluid mechanics. We will later on see that if we use this description of fluid motion, this Lagrangian motion, even the dynamical equations will appear simple. However, they will just appear simple, but they are much more difficult to solve, even though they appear simple. And also you see that in case of fluid, since there are infinite number of elements and the relative motion between the fluid elements are quite large, then to describe a fluid motion, you have to identify a large number of infinite number of fluid elements and describe their motion, which is also quite cumbersome. And also we will see subsequently that there are often the flow will be defined as steady state flow, and that describing steady state flow in Lagrangian concept will also involve little complexity. So, this Lagrangian description is usually not preferred description in fluid mechanics. Of course, there are certain cases where Lagrangian description is used, but most often another concept is used to describe the fluid motion. This other concept is known as the Eulerian concept. Okay. The Eulerian concept. What is done here is that the velocity is defined not for a particular fluid element, but at a point in space. So, velocity at a point in space and time, velocity at a point in space at any instant. That is, you identify or locate the point. Okay, this is the point x y z or x 1, x 2, x 3. So, the velocity at that point, how much it is? So, just like a field description, we are treating velocity here as a field, the velocity field at each and every point in the flow field, in the flow a certain velocity is assigned. Velocity at this point is this much. It is not fixed to a particular particle, it is fixed at a point. And any particle which passes through that point at that instant, while it is passing through that point, will have that velocity. So, here the velocity will define it by u as a function of x and t, or in our initial notation u y x I t. Now, x y z, remember in this case this x is not the position vector of a particle, but just the position vector, just a point in the space. Field approach. Also, these two approaches are often called, this Eulerian approach is also called as a cinematographical approach. It is like a cinema. You are focusing only on the screen, what is happening there, not on anything else. Here also you are focusing at a point in the flow, not to the particle, what is happening to that particle, where it is going, that is a secondary. Your primary interest is a particular position in the space. Similarly, the Lagrangian concept is also called as historical approach, where you look to the history of the element. Now, associated with this point concept, you can also have a line in the space, or a surface in the space, or a volume in the space, which are the surface in the space is known as the control called the control surface, and similarly a volume fixed in space is called the control volume. So, this concept also sometimes called as the control volume approach. Now, we will see that the dynamical relations often need the acceleration of the particle or acceleration of the body, which is quite obvious or quite natural in case of Lagrangian concept, because in Lagrangian description we are using the velocity of the particle. So, if we differentiate with respect to time, we get the acceleration of that particle. Okay. Of course, while differentiating, you have to always remember that initial position by which the particle is identified. In case of Eulerian concept, you see the velocity is assigned to a point. So, simply if you differentiate with respect to time, it does not give the acceleration of a particle. So, somehow we have to find the acceleration of a particle. We will come to it little later. So, these are the two approach, and as you mentioned that this Eulerian concept is the usual or the preferred choice in fluid dynamics. Almost for all cases, the Eulerian description is used for the fluid motion, not the Lagrangian one. Now, for a Eulerian description, if the velocity field is independent of time, that is this u I x t is independent of t, then the motion is called steady. If t is independent of t, that is flow is called steady. Flow is called steady. And similarly, if it depends on time, that is at each and every instant the velocity at that point is changing, then the flow is called unsteady flow. Three lines in flow are very important concept. The first one is called streamline, that is what we will call the first. There is no first, second and third, anyone you can call as first, second, third. So, streamlines. Streamlines are those lines to which the velocity vector at each point is tangential. The velocity vector is tangential to each and every point on the line. The lines are called tangential, lines are called streamlines. So, let us think about a line, and let us say at this point we consider a point about x location, and let us say this is the velocity vector. We may consider a small line element delta L, then what will be the relationship between u and delta L? Is the relationship between u and delta L? No relation? Yes. Complete it, yes. Cross product is 0. Okay. U cross delta L is 0. Which of course we can write agreed dx1. See this u1 as function of x and time, I am not writing that x and time all the time. Okay. It is to be understood that these u1, u2, u3 they are all functions of position and time. So, you see that this way you can find the equation of streamline. If you know the Eulerian velocity components, you can easily find the equation of streamlines. Streamlines are very, very useful to describe the fluid motions.
So, these streamlines will be function of time?
Yeah, these streamlines will, if the velocity field is function of time unsteady, then the streamlines are also unsteady. The streamlines will change from time to time. At each instant, we will have different set of streamlines. The other line are called the path line. These are simply nothing but the trajectory of the fluid particles. The path followed by the fluid particles or the fluid material elements. See, just to differentiate a fluid element which really consisting the particles of fluid, we will usually call that a material element, material volume, material surface, meaning that the volume is composed of only certain fluid particles. A material surface is a surface formed by certain fluid particles, while a volume, when you just call a volume, will just mean a spatial volume, a volume in space. So, the path lines are trajectories of fluid particles of material fluid elements. If you use Lagrangian description, this is of course quite straightforward, as you have found trajectory of various bodies in your mechanics course. The same approach when you are using Lagrangian description, that is when you are defining velocity of material fluid elements, just integrate it and get the trajectory. Okay. The approach will be similar even in case of Eulerian description. Only thing now you have to assign that, see, even the Eulerian velocity at a point is also the velocity of a material element at that particular instant when it is passing through that point. The Eulerian velocity is assigned to a particular point in space. Okay. Now, imagine a material element passing through that point at that time. So, at that instant, that material element also has the same velocity. What is the velocity at that point? Now, fix this material element, okay, and integrate. So, while in this case also there is an integration involved, but this integration is with respect to that material fixed material element. We will to illustrate this, we will solve few problems in next tutorial classes, okay, and perhaps that time it will be little more clear how to get the trajectories in case of Eulerian description. So, there is the third line which is known as streak lines, which is very important as far as physical observation of the flow. If you want to observe the flow in your experiment, this of course, you will be doing in your experimental or laboratory classes in aerodynamics, and they are called the streak lines. Can you suggest how can you see a flow of air? Okay, inject some colored dye, inject a dye, fine. Now, you will inject at certain point, you will inject a certain point, just think that okay, your injection facility is such that you are injecting at a point. Then what you will see? You are injecting dye at a particular point in the flow. What you will see? This dye will spread. Since you are injected at a point, it will spread in a line. What is this line? Okay, this line is called the streak line, but what is this line? Is it path line? See, path line is the path of a particular trajectory. Is this streak line is a path line? Not in general. For special case it can be, we will tell you what the special case, but in general it is not. See, in this case you are not looking to the single particle, that path line means you are looking to a fixed particle, a single particle as an example, okay, a single material element containing almost infinite number of molecules. But no, you are looking here all those material element which has passed through that injection point, is not it? You are looking to those element which has passed through that injection point. So, the streak lines are path of the elements which has passed through a fixed point. It is all the elements that has passed through that point. So, streak line through a point is the collection of all the fluid elements that has passed through that point. That pass through the all these lines coincide if the flow is steady. That is streamlines, path lines, stick lines, they become same when the flow is steady. In unsteady flow or in time dependent flow, the lines are separate and each set of lines changes with time. That is, the path lines also changes with time, the streamlines also changes with time, and stick lines also change with time. In our fluid dynamic analysis, most often we will consider two dimensional flow. So, now we say what exactly we mean by a two dimensional flow. When we say two dimensional flow, considering your Cartesian coordinate system x, y, z, it does not mean that there is no z direction. No. A two dimensional flow, we can say that if the flow velocity is everywhere at right angle to a certain direction, the flow velocity is everywhere at right angle to a certain direction. So, that we can define our coordinate system such that the component in the third direction or in that direction to which it is perpendicular is 0. That is, as an example, let us say that the velocity is everywhere perpendicular to the z direction, everywhere perpendicular to the z direction. Then we can define the velocity field simply by the other two components u and v, and the flow field is two dimensional. In other way, if there is a direction in which there is no change in flow, then it is two dimensional. Okay. It is not that the third direction is not there, or we are thinking about only a plane surface. No, it is that there is no change in the third direction, then it is two dimensional. And as an example, in general, in many cases this can happen if the third direction is infinite, not 0, but infinite, and that is what we will mean by two dimensional, that the third direction exists, but it is infinite in length. So, that there is no change in that direction. Even when we go for experiment, we would like to simulate or we want to simulate this two dimensional flow, and there also we can make it so that there is no end in the third direction, that is, the third direction is mathematically infinite, there is no end to the third direction. You will see later on that this we do by, in an internal experiment, by making the model fixed to the walls, so that for the flow there is no end to the body that or the model. Of course, there are certain other aspects when we come to experiments, but that is the way two dimensional flow is simulated in wind tunnels. when the model is up to the wall itself, fixed to the walls on both sides, then for the flow there is no end in the model. Model is not ending anywhere in the third direction. So, that is what is we call two dimensional flow, when the flow is everywhere at right angle to a certain direction, and the velocity field can be expressed by simply two components, and it simply means that there is no change in the third direction, and mathematically this means that the flow is infinite in that third direction. Another simplification in flow is sometimes achieved when we consider the flow to be axisymmetric, that is, the flow is everywhere symmetric about a certain axis. In terms of cylindrical coordinates x or theta, where the say x is the along the axis, this simply means an axisymmetric flow is that it is symmetric about the axis, that is, there is no change in the azimuthal direction, there is no change in the azimuthal direction or in the theta direction. So, at any x r plane the flow field is same. Of course, there are in this case there may be various situations. The azimuthal component of the velocity that may be 0, that may be non-zero. If it is non-zero, of course, it has to be fixed constant, because an axisymmetric flow cannot have a variation in the azimuthal direction. There is no variation in the azimuthal direction, that is what is axisymmetric flow. So, when the azimuthal component of the velocity is non-zero, it has to be constant. So, either it is 0 or some non-zero constant azimuthal velocity. The azimuthal velocity is known as swirl. The azimuthal component of velocity is known as the swirl velocity. Let us now come to the definition or how to define acceleration of a fluid element when you are using Eulerian concept. The acceleration of a material element in Eulerian description. In Lagrangian description, as you have mentioned, it is quite straightforward. You have the velocity of the fluid element, material element, you simply differentiate it with respect to time, or you differentiate twice the position vector of the element. In Eulerian description, it is little different. First of all, let us consider a position here. Let us call this position P. Consider the fluid element that is passing through this point P x 1, x 2, x 3, or if you want you can write x, y, z, whatever it is. This is the position at, think about a material fluid element which is passing through this point at a time t. A little time later, at t plus delta t, this element will move to certain other location, let us say to another location q here. The material element moves from P to Q in a small time interval delta t. Now, at point q, let us say the velocity at point p is u. The velocity at point p is u. Of course, it is a function of those x 1, x 2, x 3 and t, okay. But every time we will not write it. Here of course, we have to write anyway. And at q, it is a different point, the velocity is different. Now, what will be the velocity at q? You can write flow velocity at q at same time at t, okay, at time t. This is the flow velocity at q at time t. However, the material element is reaching to this point is not at time t, but is reaching at t plus delta t. So, the change in velocity of the material element velocity of the material element will be how much? This is the velocity at point q at time t plus dt. Okay. The velocity of at point q at time t plus delta t minus the velocity of at point x at time t. Now, this difference can of course be very easily found by Taylor series expansion. You are familiar with Taylor series expansion? is let us say Taylor series expansion. You have done it for say several variables or for single variables? Several variables. Okay. First of all, let us write it for single variable. The several variable is just an extension. Taylor series expansion, that is a function of x plus h is how much? Function of x, or say x 0 if you call it, x 0 plus h df dx at x 0 plus h square by 2 factorial d 2 f dx 2 at x 0 plus so on. Okay. If we take the first term on the right hand side to the left, that is what this velocity difference expression is. So, the difference can be obtained by writing all these terms. Sorry. Now, see this delta x I, what are they? The particle has moved this much of distance, that fluid element has moved that much of distance in time delta t. At point P, the fluid element has velocity u 1, u 2, u 3 or u v w, whatever you call, and in time delta t it has moved the distance from P to Q. So, the P to Q distance are simply u 1 delta t, u 2 delta t, u 3 delta t. Yes. So, this delta x I can be written as u y delta t, where u y is the velocity at x and t. Okay. This u y is this u y. Then what would be the Taylor series expansion of this? Now, instead of writing delta x I or delta x 1, delta x 2, delta x 3, we will be writing u 1 delta t, u 2 delta t, u 3 delta t. See, if delta t is a small time element, small time interval, so from P to Q we can say the distance is also very small, and over this distance the velocity is approximated as uniform what it was at P. So, this delta x 1, delta x 2, delta x 3 are written as u 1 delta t, u 2 delta t, u 3 delta t. So, what is this in Taylor series? The first term, the first derivative term. There are four variables now. There are 4 variables now: delta t, delta x 1, delta x 2, delta x 3. The first, see this delta t has of course no problem, it is simply d u y dt into delta t. Okay. For the time variable, this is straightforward, d u y dt delta t plus it will be again d u y d x 1, d x 2, d x 3, not simply d u y d x I. Okay. D u y, because for u equal to u 1 it will be differentiated with respect to both x 1, x 2, x 3. Similarly, u 2 will also be differentiated with respect to x 1, x 2, x 3. So, the index of I and index of x is not same, they are different. For every index of u, index of x will vary. If we write in as a scalar form, let us say that this is u 1, just think that this is u 1, then here you will have d u 1 d x 1 plus d u 1 d x 2 plus d u 1 d x 3, and each case they will be multiplied by d u 1 d x 1 into delta x plus d u 1 d x 2. Okay. Should we write it for 1? We will fill in this later, first write it for say 1, u 1 x I plus delta x I t plus delta t minus u 1 x 1 into t will be d u 1 d t. See, this delta t I am not writing, why we will come to it later. The second term will be, or okay, let us write it into delta t plus d u 1 d x 1 into delta x 1 plus d u 1 d x 2 into delta x 2 plus d u 1 d x 3 into delta x 3. This is the first derivative term for of the Taylor series, that first term h d f d x. Okay. This is what is this, since there are 4 variables, we have 4 first derivative terms. Okay. Plus of course, the second derivative terms we are not writing. Okay. The second derivative terms we are not writing. Now, in this delta x 1, delta x 2, delta x 3, these replace them by u 1 delta t, u 2 delta t, and here u 3 delta 3, sorry u 3 delta t. We can do that. This delta x 1 is replaced by u 1 delta t, this delta x 2 is u 2 delta t, this delta x 3 is u 3 delta t. So, all these terms have a delta t. So, the delta t comes out and this becomes sorry. The first term is of the order of delta t and the second term, without writing all details, we will simply write as something multiplied delta t square and so on.
First term delta u1 by delta t.
Delta t, yes. Okay. Now, look to these indices. You see this u1, du1, dx1. So, this multiplicating component, okay, has this multiplying component has the same index with x, while this quantity u, it has a fixed index 1, but this is u1 x 1, u2 x 2, u3 x 3. So, we have got what the general index will be. So, now we can come back here and complete this equation. This, instead of writing all those terms, we can write, if you look to that, u j d u I d x j. Agreed? This multiplying u has the same index as the x, meaning it is a sum over them, and we are getting all these three terms by writing this into delta t plus something which is of the order of delta t square and so on. So, this is the change in the velocity of the fluid element over a small time interval delta t. Divide this by delta t, and in the limiting case of delta t approaching 0, we get the acceleration. So, acceleration of the fluid particle then becomes what? This divided by delta t, you see, and then let delta t approach 0. So, you see that these terms and these terms, all these terms will approach to 0, because when you divide by delta t, this will still remain delta t. However, there will be no delta t here. So, now we get that in the limiting case of delta t approaching 0, u y x plus delta x t plus delta t minus u y x t by delta t is simply that term d u I d t plus u j d u y d x j. So, this is what is the acceleration of a fluid element in Eulerian description.
So, since we are considering acceleration here, can we assume that delta x1 is u1 delta t?
That is what we have.
So, it is contradictory also.
No, see, this delta t is a very small time interval. Delta t is a very small time interval. Okay.
But still, our assumption there is
I understand what you are saying, that if you are if there is an acceleration, how can this delta t for a small time, but if the time what we are ultimately interested is that delta t is approaching 0. So, it is a time interval of that size. So, for that small time interval, we can still assume it that. If it is for a finite time interval, of course, we cannot do it, but for an infinitesimal time interval, we can still do that. So, this is what is the acceleration. This can also be written as you see that d is a mathematical, instead of a simple derivative as an operator, this entire thing can be taken as an operator. Okay. And since this is the derivative that we have obtained while following a particular material, this derivative is often called as material derivative or substantial derivative, and it is customary to write it with this notation, a capital D. So, whenever you see this capital D within the Eulerian framework, it implies that the derivative is computed while following a particular material element.